the conductivity of 0.2 molar solution of potassium chloride at 298 Kelvin is 0.0248 Siemens centimeter inverse. Okay, conductivity is given. Conductivity means kappa. Kappa value is given in Siemens centimeter inverse unit, and they are asking to calculate its molar conductivity. Calculate its molar conductivity. So for question number 1, question number 1, kappa is given. Conductivity means kappa. Okay. Conductivity means kappa. Kappa value is given, which is 0.0248. The unit is Siemens centimeter inverse. Okay, note the unit carefully. Whenever kappa value is given in Siemens centimeter inverse, to calculate molar conductivity also called molar conductance, both are one and the same. Molar conductivity, okay, which is represented by the symbol lambda m. Molar conductivity equal to, listen, when kappa is given in Siemens centimeter inverse unit, then you must use this formula, 1000 into kappa by molarity of the solution. Okay, molar conductivity equal to 1000 kappa by molarity of the solution. Suppose if conductivity is given in Siemens meter inverse unit, then the 1000 should come in the denominator. Okay, there is a difference, keep that in mind. In the last class itself I told you that. Now, what is the molarity of the solution? Yes, molarity is given here, 0.2 molarity is given. So, molarity of the solution is also given. What is the molarity? Molarity of the solution is 0.20 molarity. Substitute these values here, that's a direct calculation. So 1000 into kappa value is 0.0248 divided by we have 0.2. Okay, so if I multiply by 1000, I'll get 24.8, correct, in the numerator, divided by 0.2. Okay, or 248 by 2, which is nothing but 124. And what is the unit of molar conductivity? Siemens centimeter square per mole. Siemens centimeter square per mole is the unit. Take down. Take the student. If kappa value is given, how to calculate molar conductivity? Right? If listen, whenever kappa is given, you should carefully watch the unit. If unit is Siemens centimeter inverse, then use this formula, that is molar conductivity equal to 1000 kappa by m. If suppose kappa value is given in Siemens meter inverse, then the 1000 should come in the denominator, that's all. Okay, all other things are same. Right? Take down. Question number 2, let me read that. The resistance of a conductivity cell containing 0.001 molarity potassium chloride solution at 298 Kelvin, okay, at 298 Kelvin is 1500 ohms. What is the cell constant if conductivity of 0.001 molar KCl solution at 298 Kelvin is given? See, what is the cell constant if the conductivity of 0.001 molar KCl solution at 290 Kelvin is 0.0146 into 10 power minus 3 Siemens centimeter inverse. Okay, it's a very simple question. How to proceed this? For this, first of all, you must know what is meant by conductivity cell. Okay, what is a conductivity cell? Students, observe carefully. Conductivity cell is a type of apparatus where the electrodes are fused in the apparatus. Okay, just for understanding purpose, let me draw like this. It is a glass tube, actually glass tube, right? And two electrodes are fused here. This is one electrode, this is another electrode. The electrodes are fused here. Okay, therefore the electrodes cannot move. Students, observe carefully. The electrodes are fused in the apparatus, so it cannot move. If it cannot move, then the distance between the two electrode, okay, L, is a constant, and area of cross section between the two electrodes, that is also a constant, because the electrodes are not moving. Okay, if the electrodes remain stationary, then the distance between the electrode is a constant, and the area of cross section is also a constant. Therefore L by A, distance by area, see, numerator is a constant, denominator is also a constant, therefore L by A is also a constant, and that constant is called as cell constant. Cell constant, and this apparatus is what we call as conductivity cell. Students, observe carefully. Conductivity cell is just an apparatus where the two electrodes are fused in the apparatus. Okay, the electrodes cannot move. If electrodes cannot move, then the distance between the two electrodes is a constant, and the area of cross section between the two electrodes is also a constant. Therefore L by A is a constant, and that constant is called the cell constant. Okay, each and every cell has a definite value of cell constant. Each and every conductivity cell has a definite value of cell constant. Okay, then now just go through the question. I'll go through the question once again. See, the resistance of a conductivity cell containing 0.001 molarity KCl solution, okay, at 298 Kelvin, temperature is given here, at 298 Kelvin is 1500 ohms. See what is given in the problem. Some conductivity cell is taken. In that cell, for this concentration 0.001 molarity, right, at 298 Kelvin, they got some resistance. What is the resistance? The resistance value is 1500 ohms. Now let me read the next line. What is the cell constant? They are asking cell constant. What is the cell constant? Okay, if conductivity of 0.001 molar solution, same solution, conductivity means kappa value for the same solution at 290, same temperature, is 0.146 into 10 to the power minus 3 Siemens centimeter inverse. Students, observe carefully. For the same cell, they have given kappa value, and they are asking you to calculate L by A. Yes, it is very simple problem. How to do that? You know very well. The formula for kappa is, what is the formula for kappa? Kappa is equal to 1 by resistance into L by A, or you can also write like this. Instead of resistance, you can also write conductance, G into L by A, where G is nothing but conductance. Okay, but in our problem, resistance is given 1500 ohms. So I am going to use this relation. What is L by A here? Since it is a conductivity cell, L by A is a constant called cell constant. So I am going to write this expression as, let me write in the next page. Yeah. So this expression kappa equal to 1 by R into L by A can also be written as, see, L by A is nothing but cell constant, so I'll write cell constant in the numerator divided by resistance of the solution. Resistance of the solution. Okay, kappa value is given in the problem. What's the value of kappa? Kappa value is 0.146 into 10 to the power minus 3. Okay, 1 by resistance is given 1500 into, we need to find out the cell constant. Okay, we need to find out the cell constant. So just multiply this by 1500, you will get the answer. Okay, so cell constant equal to 0.146 into 10 power minus 3 into 1500. Yes, student, try to calculate the value. Okay, so you will get the answer as 0.219 centimeter inverse for the conductivity cell, right? So now you know what is the meaning for conductivity cell and what is cell constant. Okay, in the last class, students, observe carefully, I have introduced the terms like resistance, conductance, then specific resistance, then conductivity, then equivalent conductivity, and molar conductivity. I have introduced these terms in the last class. Okay, resistance unit is ohm, conductance unit is ohm inverse, or you can use the unit mho, or you can use the unit Siemens. Specific resistance, okay, the unit is ohm meter, SI unit. Conductance, conductivity, I'm sorry, kappa is conductivity. Conductivity is also known as specific conductance, and the unit is Siemens meter inverse. Okay, I'm giving the unit in SI. Okay, SI units. Equivalent conductivity, the unit for equivalent conductivity is Siemens meter square gram equivalent inverse. This is the unit for equivalent conductivity. And molar conductivity, Siemens meter square per mole. Siemens meter square per mole. This is the unit for molar conductivity. Okay, take down. Resistance is nothing but the obstruction given by the material to the flow of charge. G is nothing but conductance. Conductance is reciprocal of resistance. Last class we discussed that. What is rho? Rho is nothing but specific resistance. Specific resistance is equal to R into A by L. A by L. What is specific resistance? Okay, when you fix A as 1 unit, 1 square unit, and L as 1 unit, okay, then whatever resistance that material giving, it is nothing but specific resistance. Students, resistance may vary depending upon the distance between the electrode, okay, depending upon the solution, right? Concentration, the resistance will vary depending upon the distance between the two electrode and area of cross section and all. Whereas rho is a fixed quantity for a given solution. Why? Because for rho we will fix the distance between the electrode as 1 unit length, and we will fix the area of cross section as 1 square unit. Okay, therefore rho is a constant for a given solution. Okay, then kappa is conductivity. Then we have equivalent conductivity, we have molar conductivity. What is the expression for kappa? Kappa is equal to 1 by R into L by A. 1 by R into L by A, or 1 by R is nothing but conductance. So conductance into L by A, you can also write like this. Okay, yeah. Now we can also write this as G. Suppose if L is equal to 1 cc, 1 centimeter, I'm sorry, A is equal to 1 centimeter square, then the volume between the two electrode is 1 cc volume. Okay, therefore we can also write as G equal to, or kappa, right? Kappa is equal to, what is kappa then? if L equal to 1 centimeter and A equal to 1 centimeter square, then the volume of solution present between the two electrode is 1 cc. Okay, that solution shows some conductance. It is nothing but conductivity. So conductance of 1 cc volume solution, 1 cc volume solution is nothing but kappa. This is definition for the kappa. Last class we have given. Then what is equivalent conductivity? Equivalent conductivity is nothing but conductance of a solution. Students, observe carefully. You can call it as equivalent conductivity or equivalent conductance. Both are one and the same. Okay. So what is equivalent conductivity or equivalent conductance? Conductance of a solution containing 1 gram equivalent of electrolyte. If you add 1 gram equivalent of electrolyte in some amount of water, you will get a solution. The conductance of that solution is nothing but equivalent conductivity. What is molar conductivity? Conductance of a solution containing 1 mole of electrolyte. Okay, there is nothing but molar conductivity, right? Then, and what is the expression for equivalent conductivity? Equivalent conductivity is nothing but 1000 kappa, if kappa is given in centimeter inverse unit. If kappa is given in Siemens centimeter inverse unit, then 1000 should come in the numerator, 1000 kappa by normality of the solution. What is the expression for molar conductivity? Molar conductivity lambda m equal to 1000 into kappa by molarity of the solution. Okay, yeah. So remember all these expressions. Now, what is the relation between equivalent conductance and molar conductance? Okay, relation between equivalent conductance and molar conductance. Okay, what is the relation? Relationship between these two. Okay, though it is not in your syllabus, but remember this is very useful for competitive examination. Okay, students, observe carefully. What is the formula for equivalent conductivity? 1000 into kappa by normality of the solution. Okay, you know very well normality is nothing but molarity into n factor. Normality is nothing but molarity into n factor. So if I replace this n by this, I will get equivalent conductivity equal to 1000 into kappa by molarity into n factor. And you know very well 1000 kappa by molarity is nothing but molar conductance. So I can write this as equivalent conductivity equal to molar conductivity divided by n factor, or molar conductance or molar conductivity equal to n factor times equivalent conductivity. Note down, students. This is the relation between molar conductance and equivalent conductance. Now, variation of, this is very important, student, note down. Variation of kappa, that is conductivity, and molar conductivity, okay, on dilution. How the kappa value and molar conductance value vary on diluting a solution. Okay, right. Students, observe carefully. What is actually kappa? Kappa is nothing but is the conductance of solution which is placed between two electrodes which are separated by 1 unit length, and the area of cross section is 1 square unit. Okay, or we can say 1 cubic unit. In general, it is the conductance of 1 cubic unit. 1 cubic unit, We don't know what's the unit. Unit may be centimeter or meter. If it is centimeter, it is 1 cc. If it is meter, 1 meter cube, that's all. Conductance of 1 cubic unit volume of solution, okay, is nothing but kappa. Okay, this cubic unit, you can also take it as 1 cc. Okay, if the distance between the two electrode is 1 centimeter and area of cross section is 1 centimeter square, then 1 cc volume solution will give you conductance which is nothing but kappa. Now listen carefully, student. So conductance of 1 cc solution is kappa. What is molar conductivity? You know very well, molar conductivity is nothing but kappa into volume of the solution. Okay, kappa into the volume of the solution containing 1 mole of electrolyte. Okay, so now let us take some electrolyte in a vessel. Okay, I'll take some amount of water here. Then I'll add 1 mole of some electrolyte. Just for understanding purpose, I'll take 1 mole of electrolyte. 1 mole of some electrolyte. Okay. Now listen, student. If you add 1 mole of electrolyte, you will get a solution. Okay. This solution will show some will give some value for kappa and some value for lambda m. What is kappa? See, in this solution, you take 1 cc volume. Student, just I'll draw here. You take a small volume here, 1 cc, some small cubic volume. The conductance within that solution, within that volume, is kappa, and total conductance of the entire solution is nothing but molar conductivity. Okay. Now, what will happen if I add some amount of water? Say, for example, if I add 10 ml water. If you add 10 ml water, the solution get diluted and volume will increase. Correct? If volume increases, what will happen, students? Before dilution, let me draw separately so that you can easily understand this. Observe this carefully, student. I am going to dilute the, assume that this is the same vessel. Okay, just imagine like that. Initially we had small amount of solution. Okay, that is, I dissolved 1 mole of the electrolyte, okay, in some small amount of water, so you will get a concentrated solution. Okay, this is a concentrated solution. In this solution, I will take 1 cc volume. Let us imagine that this small cubic shape, okay, is 1 cc volume, right? Now conductance within this cubic volume is nothing but kappa, and the conductance of the entire solution is nothing but lambda. Students, observe carefully. Kappa means conductance in 1 cc volume. Okay, I have drawn a small cube there. Assume that cubic volume is 1 cc. Okay, so it is an imaginary cube, right? So within that cube we have some solution. That solution shows some conductance, that is nothing but kappa. The conductance of the entire solution is lambda m. Now what I am doing, I am going to add 10 ml of water. First I will add 10 ml of water. If you add 10 ml of water, what will happen? The volume will increase. Okay. If the volume increases, students, observe carefully. The in the electrolyte, okay, let us to start with let me take a strong electrolyte. If I add water, see, you know very well, strong electrolyte undergo complete ionization. So all the molecules are already ionized, okay, in the concentrated solution itself. All the molecules are completely ionized. So we have only ions now. If I add 10 ml of water, what will happen? Volume increases, okay, but number of ions remain same because we have taken strong electrolyte. Okay, volume increases. What will happen if volume increase? Listen, student, the ions, see, in the concentrated solution, the ions are very close. Okay, but when you add water, okay, now you have large space. So ion starts to spread out. Therefore, number of ions per unit volume, per cc volume, that decreases. See student, in the concentrated solution, see this is number 1. In number 1 case, you have concentrated solution where ions are closely spaced. Okay, the ions are very close. In that case, the number of ions in 1 cc volume is very high. So kappa value is very high in the first vessel. In the first case, if I add 10 ml of water in the same vessel, what will happen? Volume will increase. Okay, see the second position, right, where volume is very high, but number of ions remains the same. What happened here is, listen, the ions get spread out and occupy the entire volume. Okay, now number of ions per unit volume, per cc volume, okay, that will decrease. Therefore, kappa value decreases. Why kappa value decreases? Because kappa is nothing but conductance per unit volume. As number of ions per unit volume decreases, kappa decreases. What will happen to the total conductance, molar conductance? Students, observe carefully. In the first case, in concentrated solution, the ions are very close, plus ion, minus ions, positive ion, negative ion, they are very close. If the ions are very close, what will happen? There will be an attraction, strong attraction between cation and anion. Okay, the ions are strongly attracted by means of electrostatic force. So the ion cannot move freely. Okay, if one positive ion moves, the opposite charge ion, negative ion, will pull that. So ion cannot move freely. You know very well, if ions move freely, then only you will get high conductance. So in the concentrated solution, we have lot of ions, no doubt. But since the ions are very close, due to strong attractive force, they cannot move freely. The moment you add water, see second case, when you add 10 ml of water, what will happen? Volume will increase. So ion starts to spread out. When ion starts to spread out, the distance between the ions, average distance between the ion will increase. Okay, distance between a cation and anion will increase. Therefore, the attraction decreases. If attraction decreases, ion starts to move little freely. Okay, so ions move freely. Therefore, molar conductivity will increase. Molar conductance will increase. If you add another 10 ml of water in the same vessel, what will happen? The volume increases further. Number of ions remains same because we have taken strong electrolyte. Number of ions remains same. What happens? The volume increases. If volume increases, ions spread out even further. Ions spread out even further. So number of ions per unit volume, okay, that decreases again. Kappa decreases. Now what happened to molar conductance? Molar conductance will increase. Why? Because ions spread out. So distance between the opposite charge ions increases. Therefore, attraction between the ion decreases. So ion starts to move again more freely. Therefore, conductance will increase. Okay. If I dilute further and further and further, what will happen? Kappa decreases. Okay, lambda m increases. So on dilution, student, observe carefully. Let me write the next page. So what is happening on dilution? On dilution, kappa value, right? Molar conductivity decreases. On dilution, molar conductivity value increases. Why kappa decreases? Because on dilution, number of ions per unit volume decreases. Okay. What is the reason? Reason is number of ions per unit volume. Per unit volume or per cc volume, okay, per unit volume decreases. Therefore, kappa decreases. Why molar conductivity increases? What is the reason? The reason is on dilution, the average distance between the opposite charge ion increases. Okay. average distance between the opposite charge ions, increases, right? This leads to decrease in attraction, electrostatic attraction. Therefore, electrostatic attraction between opposite charge ion, between cation and anion, let me write like that, cation, positive ion, and anion decreases. Okay, since electrostatic attraction decreases, ions move faster, simple. Therefore, ions move faster. When ions move faster, conductance will increase, simple. Okay, so why molar conductivity increases on dilution? The reason is when you dilute the solution, ions spread out. Therefore, the average distance between the opposite charge ion increases. Because of that, electrostatic attraction decreases. If electrostatic attraction decreases, ions move faster. Ions move freely. Okay, right? Yes, note down. Scientist Kohlrausch, Kohl, Kohlrausch, R-A-U-S-C-H, Kohlrausch, he carried out extensive research on molar conductivity and equivalent conductivity of different electrolytes. Okay, strong electrolyte, weak electrolyte, and he found that see, when we plot molar conductivity, okay, versus square root of concentration, students observe carefully. He plotted molar conductance versus square root of concentration for various electrolytes, strong electrolyte, weak electrolyte, and he found that for strong electrolyte he got a straight line. Okay, he got straight line with a negative slope. As concentration increases, okay, molar conductivity decreases. Okay, from left to right, concentration increases. From right to left, concentration decreases, or dilution. We are doing dilution. Right to left means dilution. On dilution, molar conductance will increase. Okay, right? Whereas this is for strong electrolyte. Okay, so based on this, he gave a formula for strong electrolytes. So for strong electrolyte, okay, he gave a formula. What is that? Listen, student. As you keep on diluting the solution, right to left, if you keep on dilute the solution, what will happen? The distance between the ions increase, correct? On dilution, ions spread out, right? If ions keep on spread out, the average distance between the ions will increase. At one stage, what will happen? The average distance increases to a larger extent, such that the ions move, or the ion starts to move independently. Students observe carefully. On dilution, the ions get spread out. Therefore, average distance between the opposite charge ion will increase. Okay, but if you keep on dilute, and at one particular stage, what will happen? The distance between the ion become very large. At that stage, the ions starts to move independently. There is no attraction or repulsion between the ions. The ion starts to move independently. When the ions starts to move independently, they will show very high conductance. It is called limiting conductance. Once you reach limiting conductance, further dilution of solution, okay, will make no change, right, in the conductance of the solution. And that conductivity is called limiting molar conductivity. Okay, So if we keep on dilute the solution, okay, just moving from right to left, if we keep on diluting the solution, right, the equivalent conductivity will increase. Let me draw with this arrow. Students, observe carefully. I am moving from right to left. If you move from right to left, what will happen? You are diluting the solution. If you keep on dilute the solution, molar conductance increases, then it will reach a maximum value. Once that maximum value is reached, further dilution does not make any change in the conductance, and that conductivity, that equivalent conductance, is nothing but molar conductance at infinite dilution, or limiting molar conductivity will represent by the symbol lambda m naught. Lambda m naught is called limiting molar conductivity of the solution. Limiting molar conductivity, also called molar conductivity at infinite dilution, also called molar conductivity at infinite dilution. Okay, no change will occur on further diluting the solution. That's the meaning. Okay, so based on these results, okay, Kohlrausch gave a formula for strong alkaline. What is the formula? See, molar conductivity of a solution, okay, is equal to, see, here we have some slope. This straight line has some slope. Let the slope be a. Okay, and this is the y-intercept, right? You know very well, y is equal to straight line equation, y is equal to mx plus c. Okay, so in the y in y-axis we have molar conductivity, so I'll put lambda m here. Okay, and we have some intercept, y-intercept. Let me give the y-intercept value as lambda m naught. What is lambda m naught? It is the highest molar conductivity shown by the solution on dilution. Highest molar conductivity shown by the solution on dilution. Okay, then the slope is negative, so I'll put minus sign, minus a. A is the value of the slope. Okay, and square root of concentration, which is in the x-axis. Okay, and this formula is given by Kohlrausch. Molar conductance, right, is equal to limiting molar conductance minus a into square root of c, and this formula is applicable only for strong electrolyte. Okay, take note. So here a is nothing but slope. Okay, since slope is negative, I put negative sign here, right, and the value of a depends on the nature of the electrolyte, right? Now, what is meant by that? See, you have a value for 1 electrolyte, uni electrolyte. We have a value for bi uni electrolyte, 2 electrolyte. We have 2 electrolyte. What is meant by that? Listen, this 1 represents, student, charge on the ions. Suppose if you take sodium chloride, okay, sodium ion carry 1 positive charge, chloride ion carry 1 negative charge. See, first number represent cation charge, second number represent anion charge. So cation charge is 1 plus 1, anion charge is minus 1. Don't worry about the sign, take the magnitude, 1 1. So 1 uni electrolyte. That means for uni electrolyte we get a value for A. We get a particular value for A. Okay, suppose if we take calcium chloride, see, student, calcium chloride. In calcium chloride, calcium ion charge is plus 2, and chloride ion, each chloride ion charge is minus 1. So positive ion is 2, negative ion is minus 1. Don't worry about the sign, 1. So 2 1. 2 1 means, okay, the electrolyte should be like this, CaCl2. And 2 2 means like sodium, I'm sorry, I'll take, for example, I'll take copper sulfate. where copper carry +2 and sulfate carry -2 charges. Okay, listen, the value of A depends on the nature of the electrolyte, whether it is 1,1 type electrolyte or 2,1 type electrolyte or 2,2 type electrolyte. For 1,1 type electrolyte, we get one value for A. For 2,1 type electrolyte, we get one value for A. And remember, student, whether it is NaCl or KCl or cesium bromide, whatever it is, for all these electrolytes, all are 1,1. See, all are 1,1 electrolyte. For all 1,1 electrolyte, A is a constant. For all 2,1 electrolyte, A is a constant. For all 2,2 electrolyte, A is a constant. Is this clear? Any doubt? What happens if I take a weak electrolyte? If I take a weak electrolyte and if I dilute, as discussed before, molar conductivity in y-axis and square root of concentration in x-axis. Okay, left to right concentration increases, right to left we are diluting the solution. That's the meaning. As I told you before, on dilution, what will happen? As on dilution, molar conductance will increase, no doubt. But for weak electrolyte, we never get a straight line. Instead, we get a curve like this. The curve goes like this. On dilution, right? On dilution, molar conductance increases, and after a particular dilution, see, the curve goes almost parallel to y-axis. Almost parallel to x. You'll never get a straight line. So this is the case for weak electrolyte. What is a weak electrolyte? Weak electrolyte is an electrolyte which undergo only partial ionization. Partial ionization means, suppose if I put 1,000 molecule of weak electrolyte in water, out of 1,000 molecule, say 15 or 20 molecule alone will ionize. All other molecules remains in the undissociated form. Okay, so for strong electrolyte, if we plot lambda m versus root c, we get a straight line with a negative slope. For weak electrolyte, if we plot lambda m versus root c, we get a curve instead of straight line. Okay, note down. And for weak electrolyte, we cannot find the value of lambda m naught. We cannot find the value of lambda m naught from the graph. From the graph, okay, we cannot find. I'll write like this: we cannot find lambda m naught from the graph. From the graph, you cannot find for weak electrolyte. For strong electrolyte, it is possible because we get a straight line. Correct? For strong electrolyte, I have shown you before. If you plot lambda m versus root c, for strong electrolyte, you will get a straight line. If you extrapolate the straight line to y-axis, it will cut the y-axis at a particular point, and that value gives you lambda m naught. Where lambda m naught is called limiting molar conductivity, also called molar conductivity at infinite dilution. Right. Based on the results obtained for strong electrolyte and weak electrolyte, okay, Kohlrausch gave a law called Kohlrausch law of independent migration of ions. Take down Kohlrausch law, K-O-H-L-R-A-U-S-C-H, Kohlrausch law of independent migration of ions. Independent migration of ions. Migration of ions. What is meant by that? Simply called Kohlrausch law. What is meant by that? Students, observe carefully. What Kohlrausch did was, it took strong electrolytes like sodium chloride, okay, and he took potassium chloride, and he measured the molar conductivities of this: molar conductivity of sodium chloride, molar conductivity of potassium chloride. Then he also measured the molar conductivities of sodium bromide and potassium bromide. Lambda m naught, he measured the values and he found that the difference between these two, that is lambda m naught of sodium chloride minus lambda m naught of potassium chloride. Students, observe carefully. He measured the lambda m naught value for the strong electrolyte. Okay, say for example for sodium chloride and potassium chloride, he measured the value and the value was found to be he measured the value and he took the difference. Okay, the difference gives a constant value. Okay, from that value he understood that the ions, right, ions shows a definite value of conductance at infinite dilution. Okay, what is meant by that? See, the difference between these two. Similarly, lambda m naught for sodium bromide minus lambda m naught for potassium bromide. I am not going to give you the values of this, but I am going to give you only the difference. The difference values are found to be, for in the case of sodium chloride and potassium chloride, let me give the value. The value is 24.3, I think so. One second. Yeah, the value is available actually. Yeah, actually I should place potassium chloride in front because potassium ion have higher conductance. Potassium chloride minus sodium chloride. Similarly here, potassium bromide and sodium bromide. Otherwise you will get the value in negative, that's all. Potassium bromide and sodium bromide. Okay, students, observe carefully. The difference between these two is almost equal to 23.4 Siemens centimeter square per mole, Siemens centimeter square per mole, and the difference between these two are also exactly 23.4. Right, almost. What does this value indicate? Students, observe carefully. Why he did this? Listen. Here, if you see these two electrolytes, see, chloride ion, anions are same, right? Anions are same. See the right hand side, again here anions are same. Okay, so here K plus ion and so Na plus ion, the difference of these two is given as 23.4. The same value is obtained for the difference of K plus and Na plus. Correct? Same value. That means, students, observe carefully, that means chloride ion, right, in the left hand side and bromide ion in the right hand side. Students, observe carefully. In the left hand side, this chloride ion conductivity should be same, so they cancel. Similarly, the bromide ion from potassium bromide and the sodium bromide ion from sodium bromide. Okay, at infinite dilution, these values are also same, so they get cancelled. And potassium ion conductivity at infinite dilution and sodium ion conductivity at infinite solution, if it is constant, if the two values are constant, then only the difference is 23.4 is observed for all the electrolyte. See, in the right hand side also, lambda m for potassium, lambda m for sodium, if these values are constants, then only the difference should be same, 23.4. Correct. So that means each and every ion, potassium ion, sodium ion, each and every ion, okay, carry a definite value of conductance, or it will show a definite value of conductance at infinite dilution. This is what Kohlrausch said. So what is Kohlrausch law? Let me write here. Kohlrausch law of independent migration of ions. What is meant by that? Right, the law states that, Kohlrausch law states that at infinite dilution, means don't think that we are adding infinite amount of water. No, Infinite dilution means it is the dilution after which there is no change in the molar conductance, okay, and for the dilution. That's the meaning. Okay, when you keep on dilute a solution, at one point you will reach the maximum value, right? Further dilution doesn't make any change in the value of molar conductance. Okay, so that dilution is what we call as infinite dilution. Okay, so the Kohlrausch law states that at the infinite dilution, each and every ion migrates independently. Independently means independently, that means there is no attraction or repulsion exists between ions, because the ion distance become very large, right? At infinite dilution, it states that at infinite dilution each and every ion migrates independently, okay, and contributes a definite value of conductance, to the total conductance, at a given temperature. This is very, very important. Okay, students, observe carefully. This is how we should write Kohlrausch law, right? It states that if you dilute the solution, okay, to an infinite amount, right, or if you reach the infinite dilution, then each ion migrates independently. There is no attraction or repulsion exists between ion. Each ion move independently. When the ion starts to move independently, each ion will contribute a definite value of conductance to the total conductance at a particular temperature. So each ion conduct a definite value of conductance. Okay, each ion has a definite value of conductance. So based on that, he gave a formula. The formula is this: molar conductivity at infinite dilution for an electrolyte, say for example sodium chloride. If you take sodium chloride, which is equal to molar conductivity at infinite dilution for sodium ion, because each ion will carry a definite current, definite conductance. So what is the molar conductivity of sodium ion at infinite dilution, plus what is the molar conductivity of chloride ion at infinite dilution, right? Add the two, that will give you molar conductivity of sodium chloride. Okay, this is the meaning for Kohlrausch law. People say sometime that people define Kohlrausch law in this manner, that is molar conductivity at infinite dilution for an electrolyte is equal to sum of the molar conductivities of the ions at infinite dilution. Okay, I think this is what given in the book, right? This is mathematical definition, but the actual definition is this. It states that at infinite dilution, each and every ion migrates independently and contributes a definite value of conductance to the total conductance at a given temperature. Is this clear, student? Any doubt? Chloride. See, instead of sodium chloride, if you take calcium chloride, how to write that? Molar conductivity at infinite dilution for calcium chloride. See, in calcium chloride we have one calcium ion, and each molecule of calcium chloride gives one calcium ion and two chloride ion, right? Therefore, molar conductivity means we should take 1 mole. If you take 1 mole of calcium chloride, you will get 1 mole of calcium ion and 2 moles of chloride ion. Therefore, in this case, molar conductivity for calcium ion, that means you should take 1 mole of calcium ion, you should measure the conductivity. So this is nothing but conductivity of 1 mole of calcium ion plus molar conductivity of 1 mole of chloride ion. This is for 1 mole, but each mole of that is 1 mole of calcium chloride has 1 mole of calcium ion but 2 moles of chloride ion. Therefore, you have to multiply this by 2. See, student, this is for 1 mole. 1 mole, but calcium chloride 1 mole of calcium chloride has 2 moles of chloride ion. Therefore, you have to multiply this by 2. Right? Take 2. So in general, if an electrolyte is given like this, say for example, if I give some electrolyte like this, AX, BY, and assume that this electrolyte dissociate to give X number of, I'll put some number, NX number of cations. Don't worry about the number of charge, plus NY number of B minus ion. Okay, NX number of cation, NY number of anion. In that case, we can write molar conductivity at infinite dilution for the electrolyte AXBY as molar conductivity at infinite dilution for the cation. This is for 1 mole. Since we are getting NX mole, so you have to multiply this by NX, plus molar conductivity at infinite dilution for B minus ion. This is for 1 mole, but we are having NY moles here, therefore you have to multiply this by NY. Okay, then add the values, you will get the molar conductivity of the electrolyte. Okay, take note. Yeah, I stop here. We'll continue in the next class. Thank you.